Hi, welcome to this Blender video tutorial entitled Rigid Bodies Part 3. This is the third in a series of video tutorials concerning Blender's rigid body dynamics. If you have not viewed the previous tutorials, please do, as they contain information that may not be covered here. So far, we have for the most part been using simple primitive mesh objects while demonstrating rigid body dynamics. In practice, modelers are likely to use more complex objects. There are a number of general characteristics of Blender's rigid body dynamics to keep in mind when modeling. To demonstrate some of these characteristics, I've placed in my Blender scene a flat plane object and a cube object. One rigid body characteristic concerns the object's origin. I will go to Front Orthographic View and select the cube object and go into Edit mode. I'll select all of the vertices and press the G key and move them up a bit and to the side. I'll then tab out of Edit mode. Note that when I moved the vertices in Edit mode, the object's origin point was left behind. Now with the cube object selected, I'll press Shift D and make a duplicate cube and move it to the side along the x-axis. With this duplicate object selected, I'll press the Origin button in the left tool panel and select Origin to Geometry. This places the origin point for this cube to the center of its geometry. I now have two cube objects. The left one has its origin point in the center of the geometry, and the right has its origin point outside of the geometry. They are both the same distance above the plane object. I'll go to the Scene Editor and invoke the scene's rigid body dynamics by clicking on the Add Rigid Body World button. I'll select the plane object and assign it as a passive element. I'll select both cube objects and make them active elements. I'll then play the simulation. As you can see, the two cube objects react quite differently to the collision with the passive plane object. An object's origin point acts somewhat like its center of gravity. For performance and predictability, it's good modeling practice to make sure that your rigid body objects have their origin point placed at the center of their geometry. I'll stop the simulation and go to frame number 1. I'll remove these cube objects from the scene's rigid body world by selecting them and pressing the Remove button in the Rigid Body tool panel. I'll then go to layer number 2. Here I have a passive plane object from layer number 1 and a torus object which I scaled along the X, Y, and Z axis. Note the scale settings in the notation panel. The origin point for this object is located at the center of its geometry. I'll select the torus, press Shift D, and make a duplicate and move it along the x-axis. With this duplicate torus object selected, I'll press Ctrl A and apply the object's scale. Note in the notation panel, the scale for this object is now X, Y, and Z equals 1. Applying the scale resets the scale setting back to 1, but it retains the scaling effect on the object. I'll now add these two objects to the scene's rigid body world as active elements. I'll then play the simulation. Note that the two objects react differently to the collision with the passive plane object. For performance and predictability, it's good modeling practice to apply an object's scale by selecting it and pressing Ctrl A. I'll stop the simulation and go to frame number 1. I'll remove these torus objects from the scene's rigid body world by selecting them and pressing the Remove button in the Rigid Body tool panel. I'll then go to layer number 3. Here I've added to the scene a Mesh UV Sphere object, a NURBS Surface Sphere object, a Metaball object, a Text object, and an Empty object. I'll select the Mesh UV sphere and add it to the scene's rigid body world as an active element. I'll select the NURBS surface sphere and note that all the controllers in the rigid body tool panel are grayed out. NURBS surface objects cannot be part of a scene's rigid body world. With the NURBS surface sphere selected, I'll press Alt-A and convert it to a mesh. I can now add it to the rigid body world as an active element. The same thing holds true for the metaball object and the text object. I'll select these two objects and convert them into mesh objects using Alt-C keystrokes, and then add them to the scene's rigid body world as active elements. I will select the empty object. Note this also cannot be added to the rigid body world. Even if I attempt to convert it to a mesh using Alt-C, it is actually neither a curve nor a mesh. It's still restricted from being added to the rigid body world. I'll play the simulation. I'll stop the simulation and go to frame number 1. I'll remove these objects from the scene's rigid body world by selecting them and pressing the Remove button in the rigid body tool panel. I'll then go to layer number 4. Here, in addition to the passive plane object from layer number 1, I have placed 3 UV sphere objects. Blender's rigid body objects can interact with non-rigid body objects using Blender's parenting tool. I'll select the 2 upper sphere objects. Holding down my Shift key, I'll add the lower sphere object to the selection. I'll then press Ctrl-P and make the lower sphere a parent of the upper spheres. I'll then select the lower sphere and make it an active element in the scene's rigid body world. Note that the 2 upper spheres are not part of the rigid body world. I'll then play the simulation. Note that the active rigid body sphere pulls down its 2 non-rigid body sphere children. I'll stop the simulation and go to frame number 1. I'll select the passive plane object and set its bounciness to 1. I'll then select the lower sphere and set its bounciness to 0.8. And then play the simulation. I'll stop the simulation and go to frame number 1. I'll select the 2 child upper spheres and add them to the rigid body world as active elements and set their bounciness to 1. And then play the simulation. I'll stop the simulation and go to frame number 1. I'll remove these 3 sphere objects from the scene's rigid body world by selecting them and pressing the Remove button in the rigid body tool panel. I'll then go to layer number 5. Here, in addition to the passive plane element from layer 1, I have a UV sphere object. I'll go to Front View. I'll select the lower sphere and then tab into Edit Mode. I'll go to Wireframe Display, Z key, and deselect all of the vertices. In the Properties panel on the right, I'll open up the Object Data Editor. In the Vertex Group panel, I'll press the plus button and create a new group. I'll name this Group X. Back in the 3D editor, I'll box select some of the top vertices of the sphere object. I'll click the Assign button in the Vertex Group panel and assign these vertices to the Group X vertex group. I'll then deselect the vertices. Then, while still in edit mode, I'll press Ctrl-H and select Hook to New Object. I'll then open the modifier editor. Note that these keystrokes have added a hook modifier to the sphere, with a new empty object as the hook to the vertex group X. I'll tab out of edit mode and return to solid shading display. I'll then select the sphere object and make it an active element in the scene's rigid body world. I'll then play the simulation. Note the sphere drops down along the z-axis because of the force of gravity, but the upper portion of it, the group X vertices, are locked to the non-rigid body empty object. I'll stop the simulation and go to frame number 1. I'll set the bounciness for the sphere to 1. I'll then select the sphere and the empty object and move them up along the z-axis. I'll then play the simulation. I'll stop the simulation and go to frame number 1. I'll remove these sphere objects from the scene's rigid body world by selecting them and pressing the Remove button in the Rigid Body tool panel. I'll then go to layer number 6. Blender's active rigid body objects can be affected by multiple forces at the same time. Here I have a passive plane from layer number 1, a cube object, and a wind force field. I've scaled the cube object and applied its scale. I'll select the cube object and make it an active element in the scene's rigid body world. I'll then select the wind force field. Note in the Notations Rotation panel that I have rotated this wind force field 90 degrees around the y-axis, so that the wind force runs from the minus x direction to the positive x direction. In the Physics Wind Force panel, I'll set the strength to 200. I'll then play the simulation. The cube is affected by the pull of gravity in the minus z direction and by the wind force in the plus x direction. I'll stop the simulation and go to frame number 1. I'll select the wind force and set its y rotation to 0 degrees. This causes the wind force to run from the minus z direction to the positive c direction. And note that the gravity force runs from the positive z direction to the negative c direction. I'll play the simulation. The cube falls down along the z-axis, but much slower due to the wind force opposing it. I'll stop the simulation and go to frame number 1. I'll remove the cube object from the scene's rigid body world by selecting it and pressing the Remove button in the Rigid Body tool panel. I'll then go to layer number 7. Here, in addition to the passive plane element from layer number 1, I have 2 interlocking torus objects. I'll select the top torus and make it a passive rigid body element. I'll select the lower torus and make it an active rigid body element. Now, normally one would expect that when the simulation is played, the lower torus would fall down along the z-axis until its inner surface collides with the upper torus's inner surface. I'll play the simulation. Instead of falling down the z-axis and resting on the inside edge of the passive top torus object, the bottom torus wobbles around and finally breaks out of the top torus and falls into the passive plane object. Now, the reason for this lies primarily in the torus's collision shape. Each Blender rigid body element, both passive and active, are assigned a default collision shape. This can be seen in the Physics Rigid Body Collisions panel. Here, the lower active torus was by default assigned a convex hull collision shape. The convex hull collision shape is commonly assigned by default to active rigid body elements. The convex hull shape is a procedurally generated shape that is in essence a shape that shrink wraps around the active object shape. Its center of gravity is the object's origin point. Now, this type of collision shape works very well for most objects, but it does cause some problems on curved shapes, especially those that have a dense mesh, that is, an object that has many vertices, edges, and faces at many different angles, as does the torus object. The top torus object has a default mesh collision shape. The mesh collision shape is also a procedurally generated shape that takes its shape from the object's mesh surface. Its center of gravity is the object's origin point. This is also a good collision shape choice with high-density, round-shaped objects, especially when they collide with other high-density, round-shaped objects. I'll select the lower torus object and change its collision shape to mesh. I'll then play the simulation. Now the lower torus falls down along the z-axis and stops when it collides with the upper torus's inner surface. I'll stop the simulation and go to frame number 1. There are other types of collision shapes available for selection: box, sphere, capsule, cylinder, and cone. These collision shapes, however, are all based on the shape's bounding box, and the center of gravity is the center of that bounding box. Now, you may find instances where one of these bounding box shapes provides a better collision shape than either the convex hull or the mesh collision shapes. I'll remove both torus objects from the scene's rigid body world by clicking on the Remove button in the Rigid Body panel. I'll then switch to layer number 8. Here I have a number of extruded planes that are colored yellow and the red sphere. I'll select the sphere and make it an active element and set its bounciness to 1. I'll select the first plane and make it a passive element and set its bounciness to 1. I'll select the next plane and make it a passive element and set its bounciness to 1. I'll select the next plane and make it a passive element, but I'll leave its bounciness at 0. I'll select the next plane and make it a passive element and set its bounciness to 0.5. I'll select the last plane and make it a passive element, but I'll leave its bounciness at 0. I'll then play the simulation. The sphere bounces from plane to plane. Notice, however, that the simulation is too short to complete the sphere's rigid body motion. I'll stop the simulation and go to frame number 1. Now, one way to solve this problem is to speed up the simulation. I'll go to the Scene panel, and in the Rigid Body World panel, I'll set the speed to 2. I'll then play the simulation. Note this speeds up the simulation, compressing more action into a smaller time frame. I'll stop the simulation and go to frame number 1. Another solution is to extend the simulation beyond the default 250 frames. I'll reset the speed setting back to 1. Below this, in the Scene Rigid Body World panel, is another panel named Rigid Body Cache. Here the rigid body simulation is by default set to begin on frame 1 and end on frame 250. I'll set the end frame to 400. In the Timeline panel, I'll set the animation length to 400 as well. I'll then play the simulation. The simulation is now long enough to display the full rigid body sphere's motion.